Okay. Hi. Let's start today's lecture. Hi. I'm Junyoung, one of the TAs, and it's my great honor to introduce Professor Jeehoon Kang. He's the youngest and freshest professor among School of Computing, and he's just 2 years older than me. He seems like a graduate student, I think. And he's a very friendly and nice person, so don't afraid of or hesitate to talk to him. And he got a PhD from Seoul National University. He publishes great papers every year on the best programming language conferences in the world. So I'd like to say he's another level or just light. So I'm looking forward to today's interesting talk. So please give him a big hand.
So thank you for, can you hear me back there? Okay, thank you for warm introduction. Actually, that introduction put me in a very awkward position. I really need to be very good at this talk so that I can, yeah. So 10 years ago, when I took the programming languages course in my university, the computer science as a subject was very not popular. So there were only 30 people in a very small room who took programming languages courses. But nowadays it's popular, and I'm very glad to see that. Okay, so let me start with a story of the Baduk master Lee Sedol. You know when is this event, right? Anyone who knows what event was this? So 2016, AlphaGo, that is created by Google and DeepMind, beat the master Lee Sedol by 4-1. So it is very shocking. It is really a great milestone of artificial intelligence that it can really defeat people on very intelligent game. And behind the and under the picture, there was a TensorFlow processing unit that is basically a hardware that is very different from CPUs or today's modern computers, but it is very specifically designed to defeat Lee Sedol using the artificial intelligence and implementing neural networks. So this is basically part of TensorFlow processing units from Google. So it is basically one of the main drive forces that of the artificial intelligence that advances the state of the computing to another level, basically. Google designed this CPU only within a few months. So usually hardware is really known to be very difficult to design. So it takes years and years to design a CPU or this kind of hardware. But Google took only several months to design CPU and make it in order to defeat Lee Sedol. Why? How? The question is how Google was possible to design CPU in such a short period of time. The main process is that they didn't use a common hardware description language that is Verilog, which is very low level, which roughly corresponds to the assembly language in software. But they used a very good language that is called Chisel, which is a domain-specific language that is implemented in Scala. So it has types, and it has loops and if analysis, and all the high-level constructs you learned in this course that is good for productivity of the hardware engineers. So using this good language that can better describe the microarchitecture or hardware configuration of the CPU, they could design this CPU with only several months. That is the main motivation. So here is a programming languages course slide. So this is one of the languages that changed the world, basically, or helped change the world at least. So in this class, at least you learn Scala, right? Scala there. So I guess that you have higher chance of getting higher salary. So it is something to celebrate, right? But let's move on to another lesson. What else did you learn in this class? Anyone? What did you learn in this class? Anything? Yes. Say again? I couldn't hear you. Oh, what is it? I see. I major in programming languages, but I don't know language. Sorry. Other things you learned? Continuations, right? And types or functions, first-class functions, high-order functions, and all the abstractions. Okay, basically this is a syllabus for your class, and you learned a lot of things. Basically, you learned more things than I learned programming languages in 10 years ago. So many things. Okay. I think, to summarize what you learned, I think it is the common abstractions in the modern programming languages. The types are abstractions, or garbage collection is also abstraction. Continuation is also abstraction. First-class functions is also an abstraction. So today's talk is about this abstraction. And I'm going to tell you more details or more interesting stories about the abstractions that you learned in this class. So I'm going to start with, what is this abstraction? So abstraction is basically about something complex things. Computation, for example, is very, very complex. Computation in its raw state is very, very, very complex. As you see, for example, quantum effects in the CPUs, in hardware, there are physics, there are modern physics working there. And it is very interfering with each other, and we have to deal with those interferences. For example, there, even if you are just touching a screen here, there are millions of instructions are running here, right? Millions of instructions. It is not a small number of instructions. Very, very complex program is going on, even if I'm just touching this screen. Memory stuff systems, for example, caches, or the coherence protocols, or buses, really, really difficult and extremely complex. And also, it is worsened by the emerging technologies. For example, persistent memories, or blockchain, artificial intelligence, neural networks. Everything adds up, already very complex things, and make it into another level. Oh, I learned the word from Junyoung, another level. Another level of complexity, right? It is becoming more and more complex. Computation is really, really complex. Abstraction is basically trying to envelop those complex things, for example, computation, within a simpler interface, right? It is basically, we are not going to just ignore the complex things. We are going to adopt the complex things, but the purpose of this abstraction is not dealing with the complex things in its own form, but giving a simple interface. For example, first-class functions. So the main complex thing, so the implementation behind this first-class function is, as you may well know of, function pointers, right? Function pointers and the representation of the function in the memory and all the gory details of the systems and architecture and operating systems. But in this class, you didn't care about those complex things. You just said that first-class functions is just a value. Function as a value is just a function, first-class function. And it is the only thing you wanted to know, and the only thing you want to achieve via these function pointers. So that is a typical example of this abstraction. Complex thing, function pointer, for example, is enveloped within a simple notion that is first-class function as a value. Or types. In a viewpoint, type is enveloping a very complex program analysis. So for example, the example of program analysis is like this. This variable A should be an integer. this variable b should be on Boolean. This variable should be a string or something like that. If the type is not existing, for example, in JavaScript or some very dynamic languages, in order to guarantee that a variable has a type of integer, it is very difficult to do so. It involves a very difficult program analysis in many cases. But types, static types, allows you to do that with only syntaxes. With only syntactic type checking, you can do the very complex program analysis. So in this sense, type is enveloping a complex program analysis into a simple interface that is called syntax. Good thing. So the reason why you are learning abstraction is it effectively hides complexity while exposing functionality. As I said, first-class functions hide implementation details, such as function pointers or representation of functions in the memory, while supporting what you want, function as a value. Types hide the details of program analysis while guaranteeing the safety. So as a result, it makes complex things easier, so that even though you don't know the complex things in details, you can use the complex things. You can achieve the functionality it aims to achieve. Or in other words, you can do more things than you know. Even though you know some interfaces alone, you can use all of them together to make big things. That's basically the purpose of abstraction in programming languages. Okay, so programming languages is basically about abstractions. It is first about abstractions in programming languages. But in more general, it is also about abstraction in computer sciences in general. For example, there are many abstractions in computer sciences. For example, the bottom line here exists circuits. Or maybe you can think of physics underneath here, but let's not talk about physics for now. Circuits and microarchitecture or hardware configurations and architectures or assembly languages, ISA. And on top of that, there are CS program languages, operating systems, compiler and linkers, and applications, and so on. And even inside a layer here, an abstraction layer here, it can be subdivided into multiple layers of abstractions, basically. For example, this application can be divided into libraries and executables, and executable can be divided into, for example, multiple services, multiple, for example, distributed systems, and so on. Right? So everything is abstraction, and program languages is basically about abstractions in every level of these layers of computer science. Well, the example we saw is the Chisel language that is used to describe Google's TPU hardware. TPU hardware is basically a microarchitecture result, and it is implemented in a program language that is basically an abstraction of microarchitectural things. Furthermore, program language is not only about abstractions, the concrete abstractions in computer science, it is also about unabstract itself. It is basically a meta-level proposition. It is about abstraction itself. So what is a good abstraction? What is a bad abstraction? Why or when we are saying an abstraction is good or something like that. So we are evaluating abstractions in this field of program languages. So in this class, I heard that you mostly focused on the abstractions in program languages, but if you're going to study program languages in deeper, for example, in graduate school, you are going to study these aspects as well. So this is basically one of the main take-home messages I want to deliver in this class. So please, if you're not going to focus on the rest of the talk, please just remember this slide. That's all I want. Any questions so far? Yep. Sorry. I see. So we are going. So the point I want to make is that It is about concrete abstractions, for example, types, continuations, or first-class functions. And it is about concrete abstractions in computer sciences, for example, algorithms, for example, queues, stacks, or some FIFO or clocks or something like that. But the programming language as a research field is also interested in the abstraction itself. That is, how to evaluate, for example, how to evaluate an abstraction. When we are saying an abstraction is good, and when we are saying abstraction is bad, when we are saying abstraction is correct with respect to some implementation or something like that. So in the programming language research field, we are discussing such things as well. Does it answer your question? Okay. Any other questions or comments or feedback? Okay. Then I'd like to move on to the next topic, which is basically my research. So I'm basically working on programming languages, and specifically I'd like to study systems. I mean, from hardware to operating system to system software. So that is my focus. I want to find an abstraction. I want to design an abstraction. And I want to verify the designed abstraction is correct with respect to the real-world implementation. That is basically the work I want to do, and my research interest, basically. And here, the key challenge here is that in every day, in every month, and every year, emerging technologies introduce another level of complexity to the existing, already very complex computer systems. The example I said is, for example, persistent memory. So that is basically very similar to DRAM, which is the widespread technology for the main memory storage, but it is persistent. Even if the power went out, the data is still stored there. And using this persistency as a property, we want to build more efficient systems and more powerful, more big systems, basically. But it is very complex because another factors are interfering with persistency and making this, and these interferences are really, really difficult to capture. So this is basically the key challenge. New technologies that is coming every month, every day, as more complexity to the existing complex systems. So my main strategy is designing abstractions for the new technology. My main strategy for this research interest is basically designing abstractions and verifying that the abstractions I made is actually correct. So verification is really important here because even though I say, oh, I made an abstraction of some very fancy technology, very new technology, people usually don't believe that my abstraction is really correct. It actually captures the purpose of this new technology. So in order to persuade others that my new abstraction is actually correct, we have to actually prove that. Oh, my new abstraction actually satisfies all the desired properties of the new technology. For example, it actually guarantees the persistence for persistent memory, and it actually survives the power out, even though the power input is very low, something like that. Okay, so I'm going to tell you my concrete research project in this direction. So my first project to introduce is the C semantics. You may think that C is a very old, and C as a language is a very old technology. But actually it is not quite true. I mean, C itself is very old, but recently a lot of compiler technologies have evolved, and it performs a lot of optimizations, a lot of crazy optimizations that actually changes the program language as a C. So C, for example, the old C, for example, C in the 1980s is very different from C in modern days. For example, the C standard in C11, 2011, or the C standard in 2018 are very different from the old good programming language C in 1980s. So these new programming languages are due to these compiler optimizations, And actually, because of this compiler optimizations, a lot of complexity arises. For example, compilers perform very unexpected optimizations that basically breaks the user's intention. Even though you understand the C program language in the old days and the architecture and assembly languages very well, and you try to intend something, and you try to manipulate, for example, the memory structure on the while, the compiler says that I am smarter than you, I am smarter than programmers, and it optimizes the programmer's intention very widely and breaks all the invariants the programmers wanted to intend. So there's basically a conflict between programmers' intention to use low-level features like memory layout and modern compiler optimization. So this is my PhD thesis topic that is reconciling these two and making a new abstraction that is a formal semantics of the C program languages that satisfies these two factors at the same time, supporting low-level features of C and compiler optimizations at the same time. So I basically made a new semantics for these C program languages, and it is about my PhD thesis topic. And the second thing is concurrent programming, right? So since 2005 or so, the world are full of many core systems, right? Probably all the notebooks here and almost all the phones here are running at least 2 cores. And servers in the server rooms are usually running, for example, 32 or 64 cores. More and more cores are utilized even in GPU or the TPU I just introduced and so on. So the trend here is very, very clear. We want to use more and more core. And in order to utilize these cores very precisely and accurately and efficiently, we really need to do some concurrent programming. That is basically a programming in the presence of multiple accesses to the same location at the same time. For example, multiple accesses to the same memory location. So the complexity here is that non-deterministic and strange behaviors of these concurrent programs. And the non-determinism is from the fact that there are multiple cores and they are executing on their own, and you usually do not know whether this core is executing first or this core is executing first. So there are a lot of interleaving of executions of multiple cores, and that is basically the main sources of this non-determinism. And this strange behavior is due to hardware optimizations, basically. So is there anyone who took the architecture courses? Yeah. Then you may know of out-of-the-course, right? So basically what out-of-the-course does is that it sees the instruction stream, and if 2 instructions are accessing to the independent locations, for example, this instruction is accessing this memory location, and this instruction is accessing this memory location, then the architecture and hardware sees that they are independent and they can be reordered and execute the later instructions first and before the previous instruction. Because of all these optimizations, in concurrent programming, very strange behaviors appear. Something that is incomprehensible if you are thinking just a sequential program languages. I'm not going to details about this, but it is very interesting topic, and I'm working on basically taming this complexity due to non-determinism and strange behaviors. My third project is about hypervisor. Who knows hypervisor? What is that? What is virtual management? Yes, so it is basically virtualizing the hardware environment for the guest virtual machines, basically. So there are physical machines, but you want to emulate or you want to fake as if there are multiple machines, basically, and provide the multiple machines, the virtual multiple machines to multiple virtual machines. So that is basically what hypervisor does or virtual machine monitors does, right? So the problem is that implementation of this hypervisor is almost always very complex. It may be smaller than the ordinary operating systems, but it is still very complex. But in the era of mobility and artificial intelligence, for example, I want to input my medical data here, for example, like touching some input device here, and process my medical device in here, and send the server to here, all insecurely. But in order to do so, usually you don't trust the Android operating system because it is full of security threats and full of bugs, and you usually don't believe Android. So you want to implement a hypervisor underneath this Android system and want to process my secure medical data on a separate virtual machines besides the Android. So I'm going to visit this detail in a later part of this talk. So basically, that is the thing I want to tame. Taming the complexity of the implementation of hypervisor. That is one thing I want to address in my research, basically. So this systematics is definitely about the programming language, but this and this is not that directly related to the everyday programming languages like C or Rust or Scala or Java. But still, I'm going to say my research is centered around the programming languages because I'm working on basically abstractions. And abstraction is basically the topic of programming languages. And via abstractions, I want to fight the complexities arising in these topics. This complexity, non-deterministic and strange behaviors, and this complexity, implementation of hypervisors. So do you have any questions so far? Okay, then in the rest of the talk, I'd like to focus on these two projects. I'm going to focus a little bit more on my second project and my third project because systematics project is already done. So I graduated, so I don't want to talk more about that. And this is my ongoing work. And today I'm going to tell you a little bit more about my ongoing work on concurrent programming and secure hypervisor. So I said that non-determinism and strange behaviors are the main complexity of concurrent programming, right? But concurrent programming is really important because it is everywhere in nowadays modern systems. Because widespread use of many core systems and multi-core systems mandates us to program, make system programs in a very concurrent manner. Operating systems are all concurrent programs, and hypervisors are all concurrent programs. And many libraries, many systems libraries, and for example, regular expression libraries or some, let's say, what will be, or some find libraries or copy libraries, they are all many core systems, multi-core programs, concurrent programs nowadays. And these two are, as I said, the main complexities of concurrent programs. And because of these conceptual complexities, there is a very concrete problem. There is a very concrete, complex problem that is called safe garbage collection problem. And I'm specifically targeting on this problem right now, so I would like to discuss this problem and want to share my main strategies to solve this problem in a very high level. So here is the safe garbage collection problem. So suppose that there is a concurrent linked list, basically. There's a linked list from X, Y, Z, W, blah, 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 and so on. It is linked by pointers. It is pointing to this, Y is pointing to Z, and Z is pointing to W, and so on, right? And it is concurrent in the sense that multiple cores can concurrently access this data structure at the same time. For example, thread A may iterate through this concurrent list, and at the same time, thread B may want to remove this Z node from the linked list. So it is all these accesses can be done at the same time, concurrently. And now suppose that, is there any questions? Oh, I heard from Ghost. Yeah. Now suppose that thread A wants to remove this node Z from the linked list by connecting Y to Z, right? So here, before there was a connection from Y to Z, but thread A wants to remove Z by connecting Y to W, basically. It is a very basic linked list operation, right? And the question is it okay to free Z? Is it okay for thread A to free Z immediately after unlinking this G from the linked list? Yes? No? I don't know. And this I give you my first option, and everyone else should raise your hand. I don't care. Okay, someone don't care. But I do care, so that's the reason why I'm going to tell you anyway. So actually, you should not. Because if it is safe to do so, I will not say it is a problem, right? So the reason is that concurrently, maybe thread B is iterating through this concurrent list, and it happens to point to Z at the same time, right? And if it is the case, if Z is already freed by thread A, then thread B's attempt to iterate further will result in use after free. Use after free basically means that B is trying to access this node Z after it is freed. So that is basically a bug, a problem. And this is what is called safe garbage collection problem, or safe memory reclamation problem, or safe reclamation problem or so. It is a very widespread problem in concurrent data structures and concurrent programming, because all the data structures, not only linked list, but also all the data structures that allows concurrent accesses to each data suffer from the exact same problem, safe garbage collection problem. So in order to address this problem, we really need to defer this free of this node Z until it is safe to do so, basically, right? You should not immediately free this Z, and you should defer the free of this unlinked object Z until it is safe. So basically, guaranteeing this property is the solution to the safe GC problem. So there are a few very famous abstractions for this safe GC problem. So let me rephrase this problem, and let me explain why it is complex. And safe GC problem is basically we should free objects when it is safe, and it is complex because concurrent accesses, concurrent threads may access the same data at the same time. For example, concurrent threads may, for example, thread B is concurrently accessing the same data at the same time. So that is basically the case that this describes, basically. That's the main reason why it is complex. And the key abstraction is, and it is very historical, and it dates back to 20 years ago, basically developing a library that takes care of this safe GC problem. So the design is that, the API is that, instead of freeing an object, it provides an API that is called free when safe, or free defer, or defer destroy, or something like this. That is basically freeing the object when it is safe to do so. And I'm not going to discuss the implementation details of this, but actually this is the design that is widely adopted in the concurrent programming literature. So using this function, now data structure authors are much easier to write data structures. And they basically don't need to take care of the safe GC problem at all. They just need to call free when safe function instead of free function. So in here, instead of freeing Z immediately, they can do free when save Z immediately, because it is anyway default until save. And usually these kind of libraries are very difficult and very complex, right? And that's the reason why we usually want to do a verification, verifying this abstraction, this library. Verification basically means we have to prove that if user properly uses this API, where this properly depends on the libraries, properly usually means free when safe is called in a basically a library dependent safe way, then the objects are safely freed without any, without causing any use after free problem. So because this library can be complex, we usually want to do verification. Verification of the abstraction, that usually means the correctness of this library. So there are many safe GC libraries that actually takes the job. For example, there is pointer-based reclamation library, like hazard pointers or pass debug or dot anchor. You don't need to remember the names. But all the pointer-based reclamations are slow. It is very slow. It is synchronizing unnecessarily. On the other end, there are another library that is called epoch-based reclamation. But the problem is that it is usually a very leaking memory. Usually memories are not reclaimed if a thread is behaving somewhat strangely. So all the existing garbage collection libraries have their own drawbacks. One is slow, and one has memory leak, and one has, for example, other problems I'm not going to discuss in this lecture. And I'm working on designing and verifying a better abstraction, basically a better library for dealing with this FGC problem. Fast and no memory leak, and having all the good properties of other libraries, basically. So it is developed in this. It is openly developed, so you can even read the code and contribute to it. And I'm proving the correctness of this library also openly. So you can openly see my code and my proof, basically. So that is basically the thing I'm working on concurrent programming right now. Any questions so far? Any question on this project, concurrent programming? Okay, then I move on to the secure hypervisor project. So the context is that security and privacy is becoming more and more important these days. As I said, in the era of mobility and artificial intelligence, we mostly want to process secure data here, and we almost always want to do some artificial intelligence workloads in your mobile systems, right? For example, processing medical data, or even you want to run your bank operations here, and even this camera is receiving a very sensitive and very private data that is video here, and you want to process that very securely, right? But mobile systems are not yet prepared to securely process those private and sensitive data. Android is very full of bugs, and there are many exploits. And every day, the CVE, that is a vulnerability, common vulnerability exposure database, every day, new vulnerabilities are listed, newly listed in the vulnerability database, basically. So the goal here is that instead of improving Android, which is almost impossible job, we want to build and verify a very secure infrastructure underneath this Android for processing, storing, and exchanging the sensitive and private data. That is the goal here. And as a part of this goal, we want to make a hypervisor, basically. So as I said, you don't want to put this private sensor data into this Android because it has lots of bugs with security threats. Instead, you want to make a hypervisor that is a very secure hypervisor, and run Android on top of this hypervisor. Basically, that is the big picture. And there are secure enclaves that is processing your sensitive data, and you somehow want to prove that your private data is not going to Android, but going to the secure enclave. Right? It is basically the big picture that we are conceiving, basically. And in order to guarantee this property, we need this hypervisor to be very secure. So in other words, this hypervisor should provide a proper virtualization and a proper isolation. So let me describe these two properties in more detail. Virtualization is basically the virtual machines are running on top of this hypervisor, and virtual machines are executed as if they are run on bare metal ARM machines. This as if is very important. It is not actually running on bare metal, but it is running as if it is run on bare metal. It is basically the power of abstraction. All right? It is running as if means the ARM machine itself is an interface, not a physical thing. Right? And virtual machine and the interface between virtual machine and hypervisor is basically the ARM architecture, ISA. And also, it should provide the isolation, which means that the execution of a VM should be independent of the others. For example, in this picture, the secure enclave processing should be independent from what is going on in Android. Because Android, we don't believe Android when we assume that Android is doing very crazy things. So even though Android is doing very crazy things, we want this secure enclave to process private sensor data securely, basically. So this is basically the two properties we want to make sure for this secure hypervisor. Or, in other words, this is an important thing. Or in other words, we can describe these two properties in a single programming language-like way, right? That means the ARM machine plus hypervisor and its semantics, right? It is a symbol for semantics, right? Its semantics is basically the semantics of ARM machine times n. There are n times ARM machines, basically. So that is basically saying this virtualization and isolation at the same time. And it is more concise form of them, right? So basically, this is the complex implementation. Hypervisor is a complex implementation consisting of at least 100,000 lines of code. And this is a simple abstraction, right? You don't need to care about the hypervisor when you are dealing with the hypervisor. You just know the fact that what actually hypervisors do is multiple ARM machines, and that's all. And that is basically a simpler abstraction than this complex implementation. So that is a very programming language-like way of saying this scenario. Virtualization plus isolation means this equality. Okay, so this is what we want. And because hypervisor implementation is very complex, we want to verify this equality. That means basically we want to verify that this is the correct abstraction of this implementation. So we basically want to prove the equality here, thereby verifying that the abstraction correctly captures the property of this hypervisor. That is actually what we want. And this project is with Google, and Google is basically actually building a hypervisor that is called Hyphonium, and that aims to be deployed in Android systems in 5 years. And we are trying to verify this equality and try to prove some security properties on top of that. And please visit this GitHub repository to see what's going on there. It's not that it's in very early stage, but I think it's still very interesting. Okay, this is my second research project. So do you have any questions so far?
program, with sort of like what you say that you design some program, what you call abstraction.
Right.
I mean, like all of the programs are like first some complex processes with
Right.
So why do you call like this code something like that?
I mean, yeah. So what I want to say is that if you have a very complex thing, but you split that into multiple modules in a modular way, then it gives you a better understanding of the entire system, right? And that is the abstraction I want to say. That is the abstraction we want to find out of this complex thing. And what I advocate is that this class, this program language class, is teaching you how to clearly see the abstraction inside a complex thing. And this class is also teaching the abstraction itself. That is the thing I want to tell you in this lecture, basically. So, does it make sense? Yeah, maybe I'm saying too big thing. I mean, maybe I'm saying that everything is program languages, but I'm not saying that. I know that there are many things. I want to say that maybe program language is a way of approaching to problem, way of approaching to operating system problem, or networking system problem, or security problem, or AI problem, or something like that. The main tendency of program language research is let's find an abstraction and make it modular to make complex things more easier. So that is basically what I want to say and what I want to deliver in this class, I think. Any other questions or comments? Okay. 네. So he's asking so I'm saying that I'm going to prove something and verify something and blah, blah, blah. And what will the proof or verification look like, right? So it is a little bit deep question, and I'm going to give you a little bit deep answer, but usually a system and a semantics of system is described in operational semantics, right? There are a set of states, and they are moving around and producing some events, for example, input, output, I/O, blah, blah. And we are going to say this equivalence by saying that two operational semantics are the same or somewhat related. How? The main strategy is usually called simulation. That basically means that you are going to give a relation between the states between these two systems, and let's say this is a relation R, and say that if this state transitions to another state, and this original state is related to this R, and then if there's a step and there's a matching step, that preserves the relation. So basically that is a simulation. So all the steps here are simulated here. So it is very, the most intuitive explanation I can give you for now, and that is basically the basic strategy. And there are a lot of deep theory about this simulation proof, and a lot of useful libraries that make this much easier than it should be. So if you're interested, please come after this class. Any other questions? Okay. So if you slept the entire lecture, please get up and please read these 3 slides. It is executive summary. Abstraction is enveloping complex things within simple interface. And it is hiding complexity while exposing functionality. So the main purpose of this is making complex things easier, right? And program language is a research field or the subject of study in computer science that is about abstractions. So it is about abstractions in program languages, and it is about abstractions in computer science in general, and it is on abstract itself. What is good and what is bad abstractions, how to verify abstractions, etc. And this is the most important slide, right? So please take a picture. And my research is fighting with complexity in systems by designing and verifying abstractions, basically. And I'm recruiting motivated undergraduate students very aggressively. So this is my website, and this is my email address. So thank you for this talk, listening to this talk. So if you have any further questions or comments or feedback, please give me.